Okay, we're going to take a look now at comparisons between a statistically significantly different ANOVA and a statistically similar ANOVA. We're going to use some MSLQ data, we're going to use a self-efficacy scale, and we're going to use an extrinsic motivation scale to make the comparisons. This is a flowchart that depicts the process of ANOVA analysis, depending on what happens in the results of the tests. So there assumes an ANOVA-based research question where there are 2+ categorical level data on the independent variable, and for a dependent variable, there is one interval level data set. The first thing we always do is we do the descriptive statistics, and then we test for Levene's homogeneity of variance to see if error variances are similar or different. In the case of similarity, which is what we want to happen, P would be greater than 0.05, basically telling us the curves are basically similar in shape. If P is less than 0.05, then that's a stop sign for us. We stop the work right now. We might have to adjust data. We might recalibrate. We might look at trying to equalize curves. We might make ends similar. There are some ways we can manipulate data. That's out of the scope of the work we're doing. But we're looking for P greater than 0.05 to say that, yes, the curves look similar in shape. Then we go to the ANOVA omnibus test, the F test, and if there are statistically significant differences, P is less than or equal to 0.05, then we need to do post hoc means comparisons. If P is greater than 0.05, then there's no statistically significant difference between groups. We stop there. There's no need to go further. The big point, though, we need to look at is that when we do the analysis, we run everything simultaneously. So there will be often not useful pieces of information within our results set. Let's take a look at the external motivation subscale. We're going to look at the difference between something that shows statistical significance and something that doesn't. You've already seen me analyze the self-efficacy scale. In this example, I'm going to examine the same thing, grade, but I'm going to use the external motivation subscale. So I'm going to take that data, copy it over, and paste the data into SPSS. So just following the same pattern as what I did in the last video. The box plot, simple. Grade is the category, external is the variable. These don't look as different just looking at them, and there are a few outliers here. Again, we're not going to worry about those. We'll come back and analyze through the general linear model, the univariate. Grade will be our fixed factor. External will be our dependent variable. What are the same options? Descriptives, estimates of effect, and homogeneity tests. And we'll post hoc, because we're going to set it up in advance for post hoc. We don't need to do that and come back. So everything's going to happen all at once. So here are our means, 5.5, 5.5, 5.8. These are a lot closer than the last set were. We look at the Levene's test. Again, great significance. The curves look basically the same shape. So there is no statistical significant difference in error variances or homogeneity variance. We're happy the curves look similar. When we go to the grade, we can see there's no significance here either. So therefore, that's the end. If there's no significance in the test, there is no need to look at the post hoc test because there's no statistically significant difference. Let's take a look at this on paper and see what we could cross out in the process. What I've done is I've made a printout of both the SPSS results from the self-efficacy analysis and the external motivation subscale. Let's take a look at the output and just make some markings and annotations to explain what we're actually seeing here. So the first thing we get is we get all this information about how the system is working. That's obviously not important. We don't worry about that. And then I have this case processing summary. If you recall, I actually ran some box and whisker plots when I first did the results. So we get this information, just talking about the distribution of information. Not going to need that for anything. And then here we have the graph. So this would be something we would probably want to use. We could copy that and put it into a report. Then we go into the univariate analysis of variance, which is the ANOVA test. Again, some information here that is not particularly useful because it just tells how the computer is calculating it. The between subject factors, they're just the ends. So the ends are the number of individuals. You may or may not need that. I would say you probably don't need this because it's going to appear right in the descriptive statistics right below. Grade 9, 10, 11, the means for them, and then the standard deviations and the number of individuals in each group. Okay. Next, we go to the Levene's test. We're using the based on mean, so we've got some extraneous information we're not going to worry about. There's the Levene's statistic, the F, degrees of freedom, 2 and 125. So we write that F, 2 comma 125 equals 2.05, and then P equals 0.13, or alternatively, you could write, because there it is, or alternatively, you could write P is greater than 0.05. So either way would be an acceptable way to write that. We see 0.313 greater than 0.05. We know this passes the Levene's test, so we go to the next step. Okay, there's also some additional information that's left over from the Levene's. We don't need it. Okay, so now in the ANOVA omnibus, the test between subjects of facts, that's the ANOVA omnibus. There's lots of information here, again, that we really don't need. But so we don't need the corrected model line. We don't need the intercept line. We need the grade. We need the error. And we need the total. We're actually using the corrected total in this situation, because that's how these things are going to add up. This should add up to this. So if you were presenting this as a table, that's the information you would want. Now, in my results here, we can see the significance is 0.035, which means statistically significantly different, meaning we're going to go on. And we can write that as F2, F2 comma 125 equals 3.43. P equals 0.04, or P is less than 0.05. Either way is fine for this. So there is significance. When we find significance, we have to go on to the post hoc tests. And here are the post hoc tests. And in the post hoc test, we're comparing 9 against 10, 9 against 11. And let's see what matters here. So 9 against 10, there's the mean difference. Significance, no significance, so that one doesn't matter. 9 against 11. There's where the difference is. Grade 9 is different from grade 11. 10 and 9 we've already done, so this is a useless line for us again, because it's just a repeat. So 10 versus 11, that is useful, but it's not significant right there. And then these guys are both repeats. So this is information we would not need. So we need these three pieces of information showing that 9 and 11 are significantly different from one another. The subsets are set up that way too. We can see these two are statistically similar and these two are statistically similar, meaning this one and this one are different, which again is the same as before. 9 and 11 are different from one another. Now we're going to do the extrinsic motivation. Again, it starts with the way the computer's calculating information, so we get rid of that. Not important to us. The case processing summary sets us up for the box and whisker, so we don't need that. Then we have the box and whisker. Again, we have these outliers. These are the outliers here. We're not going to worry about those because it doesn't matter right now if it passes all the other tests. So this we can look at for descriptive purposes. Gee golly, they look similar. Then we get into the analysis of variance. Computer calculations we don't worry about. Between subjects we don't worry about. And then we have the descriptives. And you would have done your descriptives using the frequencies to have more information, but this gives just the summary for the purpose of what we're doing. We're looking at 5.5, 5.5, 5.8. Are they similar or different? So that just gives us a description. It goes hand in hand with the box and whisker plot. Now we do the Levene's test, and we're doing it based on mean. So we'll get rid of these. And we'll see that the Levene's test is greater than 0.05. So we know there's no statistically significant difference in the shapes. If we were writing that out, as we did the other ones, F2, 127, 127 equals 0.70. right there. And then the P equals 0.50, or P is greater than 0.05, whichever one you prefer to write it on. Then we get our ANOVA results. And again, there's extraneous information here too. We don't need this. If we're reporting, we don't need this. We don't need this. We're just using this. But now here's the dealie on this one. Significance 0.625. So F, comma 2, comma 127 equals 0.49 to 127.49. P equals 0.62, or P is way greater than 0.05. So this says there are no statistically significant differences in the grades when comparing the external motivation. Therefore, any of this stuff that comes afterwards, we don't need because there's no significant difference. So there's nothing to check. By the way, just to see, the subsets are all together. They're not separated at all. So there's no further interpretation. Once you get the P is greater than 0.05 on the omnibus test, you're done. You stop. It's over. So I hope this provides some guidance on tackling questions with ANOVA when there is and there is not statistical significance.